Okay, we begin this session. This is a topical plenary sessions and on the reacting flows and combustion, and we will have three presentations. The first one will be given by Dr. Junjun Guo from King Abdullah University of Science and Technology. He will talk about the high fidelity simulations of pressurized inverse diffusion sooting flames. Let's welcome Dr. Junjun Guo.
Hello, good morning. So, okay. So, good morning, everyone. So, my name is Junjun Guo, research scientist in King Abdullah University of Science and Technology in Saudi Arabia. So, it's my honor to give a presentation here. So, today we'd like to share our recent work regarding the soot modeling in the pressurized inverse diffusion flames. So before I start in the presentation, I would like to acknowledge my colleagues who are directly contribute to this talk. So I'm working with Professor Hong Ying and also my colleague Dr. Ayuka Cornela, and we're working on the numerical parts. And Professor William Roberts and Dr. Peng Liu, they are providing the experiment data for validation. So this work also involve part of the project with L products, and all the computational resources are provided by KAUST supercomputing laboratory. So my presentation has the following 4 parts. So let's begin with the motivation. So hydrogen is now is very popular. So here's the very simple field is already studied in the combustion community for many years, and recently considering the carbon capture, so and as a carbon-free fuel is become more and more popular. So based on their production resources, it can be classified by different colors, like green hydrogen, blue hydrogen, green hydrogen. For the green and blue, they are using the fossil fuel, for example, the natural gas, and the difference how the treatment of the CO2. So if you have the carbon capture and then you produce blue hydrogen, and then when you're using the renewable energy, and then you got the green hydrogen. But nowadays, in the worldwide, most of the hydrogen is still the blue hydrogens. So there are different ways to produce blue hydrogen using natural gas, oil, and coal. So for example, so here I list the 4 different technology. So the pyrolysis and different way of reforming. So the steam methane reforming, autothermal reforming, and partial oxidations. So you see that from the reactions, you see the autothermal reforming and the partial oxidation, they involving some partial oxidation. So there's some heat released. This means you don't need to provide external heaters. And then all the flue gas is easy to achieve carbon capture. So both technology is more and more popular nowadays. So we look at more detail about both technologies, you will find some similar configuration. Like, for example, the oxygen is coming from the center and surrounded by the fuel, and then form a flame to achieve partial oxidation of the fuel. The same configuration also used in the partial oxidation. So this means both technologies use the inverse diffusion flame configuration. But in this scenario with partial oxidation, so we have gasification conditions. There's a risk to form soot. this carbon particle, and then he will reduce the equilibrium efficiency and also have some negative impact for the downstream equivalents. For example, the catalyst and also the quenching waters. So what is the, So what is the soot? So it's a very old topic in the combustion community. So in case you are not familiar with this, I will briefly introduce. So soot is a carbon particle resulting from the incomplete combustion of the hydrocarbons. So through many years study, we are already identified there are some multiple pathways to form the soot. For example, from the gas phase, through the nucleation process to form some the first particle, and then through surface glue condensation, coagulation, some larger particle, and finally be maybe oxidized by OH or oxygen. And this figure shows the soot morphology captured from different flame locations. You see that it's very complicated, and the morphology is also changed through the combustion stage. So the objective of our study is try to understanding the soot formation process in these reforming conditions based on both numerical and also experiments. So in KAUST, we have some in-house experimental. So firstly, we focus on the laminar case because this flame is easy to control, and we can get as possible as experimental data for validation. So this is the inverse cold flow flame burner. So we provide oxygen in the center and surrounded by the fuel. So in this study, the fuel is the methane, which is used to represent the natural gas. And this is a basic flame image we got. And then this is the experimental setup. We can using the PLEAF for the OH measurement and also the soot volume fraction, and also the PLEAF is for the pH, which is a polycyclic aromatic hydrocarbon, which is the soot precursor, so it's very important for soot studies. And also we have the soot measurement. We mostly focus on the soot volume fraction, also the particle size. So here is the numerical model we are using. So we use OpenFOAM, and then but we do some modification because the default solver cannot well handle the transport part. So we develop a model based on the OpenFOAM, and then for the thermodynamic property and also the kinetics and transport, we use the Cantana. So we have a coupling between the OpenFOAM and the Cantana. And then for the gas phase mechanism, we use actually this reduced Kaus-Armco pH mechanism, which still have 115 species. So this is still a very detailed mechanism. And we use method of moment for soot modeling. We're considering a detailed soot pathway. So here I give the basic Gaussian equations for the momentum, species, enthalpy, and moments. So since we are more focused on the soot, so here I will introduce the soot model we are using. So for soot dynamics model, so the stochastic model is most he can provide a very accurate result, but it's very computationally expensive. It's very hard to use in the CFD, especially for the turbulence flame. And then secondly, you can have the sectional method, like his trade-off of the computational resources and also the accuracies, but it's still expensive for CFD. So here we use the method of moments. So in this model, instead of solving the number density function, we only solve the moments of the number density. So we'll got some statistical parameter for the soot quantity. For example, the number density, the mean particle diameter, and the surface area and the volume fractions. And then for the soot, we also need the soot kinetic model, including the inception, adsorption, and the surface growth. So here, I would like to emphasize this recently proposed so-called reactive inception model. So here the most important things we involve the radicals in the inception process. So here I also put the classical model, which is the widely used in the CFD, which is very simple. And then in the later, I will also compare both model and then show the result in the inverse diffusion flames. And then for the surface growth and oxidation, this is the typical Haka mechanism, with hydrogen abstraction, carbon addition. We didn't do the modification. So here is the computational domain, considering this axis symmetric configuration. So we only run a 2D simulation, and then we have 5 cases with pressure from 3 to 20. We didn't simulate the 1 bar case because in the 1 bar case there we didn't detect the soot. So yeah, so in the so the boundary condition is exactly the same with the experiment data. So we fix the mass flow rates for all ignites. So this means when the pressure increases, the velocity is decreased. And then firstly, let's look at the flame structure. So this figure is the flame imager capture in the experiments. You can clearly see that there are 2 regions. The first is the blue region, which represents the main reaction region. And then the second one is this orange or yellow region. This is coming from the soot radiation with the high temperature. So you see that there are a lot of soot emission. So in this region, you didn't see this yellow or orange. This is just the temperature decrease caused the radiation decrease, not the soot oxidations. So here we also put the numerical results. So the blue one is the OH, and then the orange is the soot volume fraction. So we basically capture these 3 structures, and then you do see that soot emissions. We also do some quantitative comparison with the flame height using the location of the peak OH in the flame sentinel. You see that we basically capture this linear decrease with the decrease in the flame height, but slightly over predicted. And then this decrease is due to, since we increase the pressure, and then we will increase the pyrolysis rate, and you will also find that peak temperature is also increased. And then the important thing is the pH, which is the soot precursor. So here it's difficult to do the quantitatively measurement for the pH. So they provide the pH proof, which is actually this single is linear relative to the pH concentration. So, and then different wavelengths also depending on different sides of pH. So based on the previous study for this 450 wavelength, we use compare with the actually this is the A3, which has 3 aromatic rings. So basically we capture this structure. So firstly, the pH is continue to increase with the flame height. And also when the pressure increase, you see that the pH is more concerned to the flame sentinel. This is due to the change of the flame structure by the buoyancy effect. So for the spatial distribution is well predicted, and also we do some comparison with the change of the concentration with the pressure. So you see that you will clearly find this linear relationship with the peak concentration with the pressure. This is very important. This is much different from the normal cold flow flame, which the fuel is in the center and then the full oxidation is achieved. The pH is found is a power loss. So this is the main difference between the inverse diffusion flame and the cold flow and the normal cold flow flame. And then we look at this soot formation. So here is the soot volume fraction spatial distribution. So it's also only half of the flame. So you see that this dashed line is the flame center, and then the left part, this is the measurement, and then these simulations. So first thing you see that the soot is increased at the beginning, but is keep unchanged in the downstream, in the post-flow regime. This is some new phenomena we observed in the inverse cold flow diffusions. And then our simulations also capture this simulations, these observations. And also you found the same observation with the pH, and then the flame, the soot is more close to the flame center lines. To do some more clear correlation, we plot the soot volume fraction, the mass fraction of pH and soot, as well as the measurements along the flame height. So here we normalize by the flame height. So you see that in the this 100 means this in the flame region. You see that the soot is increased in this region, and then it's almost keep unchanged in here. But the pH you find is continue to increase. So in the simulations, the black line is what the model we use in this study, which is a reactive inception model. We capture this flat region. But if you use a traditional inception model, which shows this dashed line, it will continue to increase soot. The reason behind that is in the classical model, you didn't involve the radicals. So once they have the pH and the temperature is also favored for soot creation. So that's why you will got high soot volume fraction. So you also see that in the literature results in the right figure, this blue, the blue dot. So you see that they much over predicted the soot, especially in the high pressure conditions. So here, this linear relationship is also well captured in the simulation. And then next, we will try to find the reason why we got this linear relationship with the soot and also with the pressure. So we put some important parameter like the mole fraction of some pH, this 3 aromatic ring and then 2 aromatic ring, and also the concentrations and the density in the same location, also the radical. They all present this linear relationship. And also, if you look at the formation pathway of the soot and also the oxidation and also the dimerization, they all the linear relationship will be found. So this means that this linear relationship between the soot and the pressure is originally coming from the increase of the pH concentration with pressure, which is directly changed by the density increased. So apart from the pressure effect, we also studied the CO2 additions. So there are two reasons. One is like we can we add some CO2 in the field site, and then we can convert this CO2 into some useful syngas. So the literature result already show that adding some CO2 can reduce the soot formation, but the reason is not clear. So here we introduce one more species, which is the FCO2. He has the same thermodynamic with CO2, but he will not involve in the reactions. So by introducing this, we can distinguish the thermal effects and the chemical effects. So you see that both thermal effects and chemical effect can reduce the soot, but the chemical one has higher impact. And then those effects can impact all the pathway, including inception, adsorption, and the surface growth, and also oxidations. So we further study why these chemical effects coming from. So we do the pathway analyze for the pH formation. So we, for example, we take the benzene as an example. So we identify that the H radical has a very important role in this pH formation, as well as the soot. And then we do some sensitivity analyze. We found this reaction with CO2 plus the H to form CO and OH. So once you add CO2, the OH is consumed by the H radical is consumed by CO2. That's why you add CO2 and then you reduce the radical and then you will reduce the pH. Finally, you got less soot. So this is the reason. So the above result is all coming from the laminar case. Recently, we're also doing the turbulent sooting flame, but now so far we still focus on this normal cold flow flame, which the field is from the center, because we didn't find the inverse cold flow flame experiment, because in that flame you will have a lot of fuel, a lot oxidized, and then you also have a lot of pollutant emissions. So it's very challenging for the experiment. So here we trying to study, also look at the pressure effects. We have two methods for the combustion model. One is the typical is the flame progress variable model. So here what we do is like we need to generate some flame list which consider the including the soot information, but basically like the flame master, we cannot get the soot. So what we did is we implemented the flame controlling continuous method in the open smoke, and then we can get this ice curve for the soot information. But we also realized that this pH chemistry is very high, so it's not. So the classical flame list model is not working so well. So we also have this new path model, and then this new path model to better considering the different multi-scale time scales. So here I put some simple results using the FPV. So we got the suitable fraction temperature, and then for the pressure scaling, we can basically capture this pressure scaling, but we much under predict the soot. So this means there are still much work need to do in the turbulent cases. So let's go to the conclusion. So based on our simulation, so from the modeling parts, this reactive inception is very necessary to capture the soot's behavior in the inverse cold flow flame. And now we can also capture the linear relationship with the soot and pressure, and we provide the explanation for the soot suppression by the CO2 additions. And we also seek more experimental data for the turbulence inverse diffusion flame, and then to do more like to validate all the finding from the laminar can also be is it true or not in the turbulent cases. So yeah, that we will end. Thank you. Yeah, actually, this is a good suggestion, but basically, for these laminar cases, we didn't do that analysis, but we're planning to do that in the turbulent cases. I think that's maybe more interested in the turbulent conditions.
My congratulations for your presentation. My name is Domenico Lei. You mentioned that you do the coupling between OpenFOAM and Cantera software to do the combustion simulations.
Yes.
Could you please elaborate on the argument? Why do you do so, and what advantages have you seen? Thank you very much.
The reason to that is because we are firstly trying to use like the default, like the reacting form in the open form, but we found that there are two like disadvantage. The first is the transport. They cannot well capture these molecular transport in this reacting form, and the second is the reaction, like the solver for the reaction source. So we found the CVOD is slightly better than the default one in the open form. That's why we developed our own solver. Basically, this coupling with the coupling the open form with the Kata is not new in the community. There are already different group using this method.
Thank you very much.
Thank you.